Hello, everybody. My name is Dulguun Dorjlkham, and I'll be presenting to you on drug-induced liver injury compound detection using convolutional neural network. These are the table of contents: introduction, data set, introduction, method, and results. Before we move on, I want to introduce to you our problem statement and why I chose to conduct an experiment on this topic. My experiment involves around liver injuries. As a multifunctioning organ, liver is responsible for not only breaking down a foreign object that enters our body. The liver also controls our energy management, is a part of our immune system, and even controls our hormone management. So it's a very vital organ that controls our survivability. Because it's an organ that deals with a lot of foreign objects, it's susceptible to a lot of injuries and prone to compromises. One of the main compromising factor or a contributor to this compromise is injury called drug-induced liver injury. Whether from a chemical structure of the drug itself or an environmental factor such as patient's characteristics or environmental factors, prescribed drugs are one of the most largest contributors to drug-induced liver injury. In this project, we will be looking at DILI caused due to drug-induced liver injury due to drug chemical toxicity. We'll be looking at chemical structures of the drugs to determine whether that drug will be drug-inducing or non-drug-inducing. No, DILI injury-inducing, excuse me. Similar research have been taking place before, while using drug chemical structure was represented through molecular fingerprints or embedding methodologies. For example, a research on using molecular fingerprint embedded features to predict the drug-induced liver injury potential in drug was done by Fo, showed a great result with over 90% accuracies and above 95% AUROCs. This task is important not only to preventing drug-induced liver injury for patients, but also for drug development process and pre-marketing screening. Now, unlike this previous methodologies, I wanted to use molecular structure shape as an input file for our prediction. People use molecular fingerprints to look or a lookup table to describe the molecule. I wanted to know if it was possible to take a picture of a molecule and feed it into a convolutional neural network to see if it was able to predict the drug-inducing nature of the compound. So, for example, I would say DILI positive acetaminophen, a very popular drug-induced liver injury compound, while amikacin, which is a bacterial drug which does not induce liver injury. So I would take a picture like this to the convolutional neural network. For dataset introduction, I have used a dataset called DList. Now, it's a dataset created during the research project named Drug-Induced Liver Injury Severity and Toxicity DList, binary classification of 1279 drugs by human hepatotoxicity. The dataset was created contained in which 768 were DILI positive and 511 were DILI negatives. In total, 1,279 drugs were created in DILIs. I'll be only using 1,139 drugs, as it was only those drugs that were available for me to convert it into a picture of a drug molecule, such as the one that is shown on the right. I have used, each drug name were passed through a Cactus NCI API, which in turn provided a SMILES representation of the drug. SMILES representation is basically a letter representation of molecular structure of that drug, such as here as shown. By using RDK library in Python, I was able to convert these SMILES code to mol block representations, which was then converted into RGB 3-colored 3-channel image of the chemical itself. Now, stratified split ensured clean and even distribution of negative and positive labels, and training and test dataset were divided into 80 and 20 ratio. Training dataset was then further divided into training and validation with 80 to 20%. For pre-processing, no other augmentation or transformation were applied to the picture files except for the resizing of the picture to 240 to 120 pixels. For the reason for no augmentation or noise was added was because we can ensure that the image, a new image or new chemical, when it is being added to the model, we can ensure that the format can be similar or exactly the same as the every other data set samples. Hence, no augmentation or transformation was added to the picture. As we can see here, we have a methods, and I have used convolutional neural network. Specifically, what I have used was I used a convolutional block, which is a convolutional layer stacked on top of each other. So 3 stacked convolutional layer and a linear layer, basically a very simplified version of feed-forward neural network, and use the sigmoid to determine whether that results were dilly positive or dilly negative. So the picture with 3 channel would go into this model and be determined positive or negative. Going deep into what exactly my convolutional block was, I used the convolutional block and ReLU activation function to reduce the negatives of that convolutional block output. I used the max pooling to reduce the dimensionality. So first, the image would have 120 to 120 pixels. Then I would use max pooling to reduce that dimensionality. And then I would then use a batch normalization to standardize our inputs and repeat this process 3 times to and increase the channel every time. So first I have 3 channel. I use convolutional layer to increase to 32, 64, and 128. which then is converted into not converted, flattened and inputted into a basic feedforward neural network. I have used the binary cross entropy, which compares each of the predicted probabilities to actual class of output, which can be either 0 or 1, since we are using a binary classification. I've also used Atom Optimizer. I didn't tinker with the hyperparameters such as weight decay and so on and so forth, and I only used learning rate, and others were all default values. For learning rate, I found out that 0.0005 or 1 to the power of 10 minus 5 were the best learning rate, as anything more than this value were leading to overfitting, and anything below was leading to extreme amount of training time. Excuse my stuttering. So for the results, I have ran it for 30 epochs with 128 small mini batches. The data shown on the left side, the graph shown on the left side represents the red line as the training loss and blue line as the validation loss. As we can see, around epoch 8 was the state where the validation loss was at the lowest. Hence, we determined that the best epoch was 8. And if we can see the accuracy as well, the training data set goes to 99.97%, immediately overfitting and biasing on the training data set, while the validation is 61% accuracy on the 8th epoch, with the loss of 6.69. The flattened result went through a lot of conversions, and due to that, the result test was that the accuracy was not that high, with 0.57, with a loss of 0.686, with AURC and AOPRC both showing around 0.5 to 0.6 results. One might say, looking at this AURC graph, that this model does not know or is incapable of determining whether a compound is dilly positive or dilly negative. But as a conclusion, I want to mention that it is because I have used a simple linear stage method, such as FFNN. Method was unable to determine differences between positive and negative dilly compound. The way I could improve this model is by first reducing the channel number. So I start up with RGB 3-channel picture. I may need to reduce it down to gray color, binary color picture, so that the model is able to focus on the picture and shape itself, not the colors. After the convolutional accuracy of my model, here are the references, and Thank you for listening to my presentation. That's the end.